everyone. Welcome to my talk. My name is Vasia Kalavri. I'm part of the Flink project. And I'm also a PhD student at KTH in Stockholm. And today I'm going to talk about automatic detection of web trackers. This is a project I did while I was an intern in Telefonica Research last year. So the talk will not really be about the results and how we finally, if we really detected the trackers or not. It's more like sharing my experience while trying to solve this problem, and like lessons learned that I think you will also face if you work with data trying to solve a similar problem. So let's start with Telefonica. It's this amazing building by the sea in a sunny place where it's always warm and nice. But apart from that, they do really cool research there on a lot of topics like computer networks, security and privacy, distributed systems, multimedia, recommender systems, and so on. So I spent 6 months with them, and one of the projects I did was what I'm going to talk about today. So maybe you've heard of this quite popular quote that says that the best minds of our generation are actually thinking how to make people click on ads. I don't know if that's true, if it's the best minds of our generation, but we all know that ads is still how big web companies make their money. And I guess that's okay to some extent. But the problem is that these ads, in order to be successful, they have to be personalized. And in order for them to be personalized, they have to have information about who is browsing a certain page. So there are some legitimate ways to do this and get this information, and there are some more questionable ways to do this and get this information. So, for example, if you log into a website and you know explicitly that you are sharing what kind of things you're buying or your preferences on the site, then you see a personalized ad and you think it's okay. But usually there is some background activity that users are not really aware of. And I'm referring to web tracking. So what happens is that not always, sometimes. When you visit a website, in the background there are some third-party connections that open. And these third-party connections do some cookie exchanges with your web browser. So they retrieve data from you, and they build a profile that they share with the ad servers, so you can be served more personalized ads. And maybe you're thinking, okay, so what? I gain like better ads by that. Well, the problem is that studies have shown, and I'm sure you have felt it too, that ads can be like really creepy, especially if you don't know how they found out that you like something, or maybe you did something in one site and then you browse Facebook and you see, I don't know, things about something sensitive, information that you haven't explicitly shared. So ads can be creepy if they're too personalized and if you don't know where you share this kind of information or where it's going to be used. And moreover, well, we have proof that governments use this kind of techniques to spy on people. So I can keep on going on about why tracking can be harmful, but this is the motivation. So the motivation was that, okay, we have all this background activity happening, can we somehow block it so that it doesn't happen? Because the problem is that it's not only that it's a background activity that happens, but the most terrifying thing is that you might be visiting one website at one time with one IP, and then there is like some cookie exchange, and then maybe you're visiting a second website with a totally different tracking service and a totally different IP address. But it has been proven that if it happens that you visit another website that has both these tracking services, they can actually match your profiles and you can be uniquely identified. So if you want to be more scared about this, read this paper. It will really scare you out. It did to me. So the motivation is that, OK, this is happening. We don't really see it as users because it's in the background. Can we somehow stop this from happening? And the setup that we had at this Telefonica project was that we had a proxy that was already between the mobile users of Telefonica and the outside internet. And this proxy gives several services like caching and some mobile services. So we thought, OK, maybe we can use this proxy also to check the connections before they go to the outside world. And the ones that go to trackers, we stop them, and the ones that go to legitimate sites, we let them be. Now, the problem is that if you want to block a request to a tracker, you have to know that this URL is a tracker. And how do we know this? Currently is by using crowdsourced lists that basically have a list of tracker URLs that say this URL is a tracker, and so on. But these lists have several problems. So first of all, they're not very frequently updated. If you see, they're updated something like once per week, maybe, or the updates that they have are like really, really small. But the biggest problem is that we don't really know who updates this list or based on what criteria they blacklist URLs. And they might miss trackers that are dual role, so they might be also legitimate and also tracking, but you don't really know. And the problem for the application developer for us was that we had to have this list updated frequently and then manually match every request that we were getting to that list. But most importantly, I'm sure you saw the news at the beginning of the month that you can buy your way into this whitelist. So there are several companies that were doing this for a while, paying AdBlock to whitelist them. And then this news broke out that AdBlock was sold out of nowhere to somebody that we don't know who it is, and for money that we don't know how much it was. So people are starting to realize that, maybe there are some whitelisted trackers there, and maybe it's just my imagination having the blocking there, and there's stuff that we don't know. So based on all of that, we wanted to build an automatic classifier that would say this URL is a tracker or this URL is not a tracker without relying on any kind of crowdsourced list. So our goal was to take data from that mobile proxy that we already had in place, analyze it, and build a classifier that would tell us if a URL is a tracker or not. And our initial idea was that we can probably exploit fundamental properties of trackers. And basically, we wanted to exploit structural properties. For example, in which position in the network they are compared to other pages. And operational attributes, like how much data they send over the network or how long it takes for them to reply and things like that. So can we do this? We started brainstorming, trying to figure out basically features that would help us distinguish trackers from other pages. And the first thing we started thinking is like, OK, first, if we want to distinguish the trackers, they have to somehow be similar. But how are they similar? Do they have similar network structure or receive and send similar data? Or what kind of latency do they have? And if they do have similar characteristics like that, how do they differ from all the rest of the pages in these ways? And are they mainly connected to other trackers? And this is how we started approaching the problem. So this is where we started seeing a very clear goal of what we wanted to do. But as in any data project, I think, the road to the goal was not clear at all. So we had so many paths we could go to. And this is actually what I'm going to talk about, how we went left and right trying to find the right solution, and how we finally ended up to the goal. So when you have such a problem and you don't really know how to approach it, you have a bunch of algorithms that might work or not. You have to tune them afterwards. You have some idea of what kind of features you want, but not for every algorithm, every feature works. And then you have to combine all of these. And this takes a lot of time and trial. So, of course, where you start from is your data set. So the data that we had was user logs, augmented logs from HTTP requests that went through the proxy. So we had some information there, like who did the request, like an IP, to which address, and then what kind of connections opened from that request, how much data was transferred, and the latency and some other things. So we had 6 months of data of this type, which was around 80 million records of this type, 3,000 distinct users, around 2 million distinct URLs, and we had already 4,000 tagged trackers using one of the lists. So of course we started doing some basic dataset analysis to see what we can find in there. So things like how many of all these 80 million requests, how many requests are to trackers? Or and from these trackers, how many do we have per user or per request or per website? So do websites that are do popular websites embed more trackers than non-popular websites? And do same topic websites have the same trackers, or do they have different ones? And well, yeah, if you and me go to the same website, do we actually get connected to the same tracker, or is that also personalized? So a lot of questions. And then from the operational side, do tracking requests take longer than normal requests, or shorter? Or do they send more or less bytes? Or maybe nothing. And like how many connections do trackers themselves have on average, and so on. And actually this analysis might seem like a lot of work to you, but we actually did this with the dataset API in like 1 day. So we were very fast, really fast. We could like have an initial idea of our data and what is going on, and start like moving to the algorithms really fast. So pre-processing was fast. So the first main idea we had was that, okay, we have requests from a source page, and then we have all the requests that open from that page. So we modeled this data as a bipartite graph, where the first mode, the first group, is the URLs that the user explicitly went and clicked, and the pink one is all the requests that opened from that action. So the idea was that we take this graph and we try to analyze it, and somehow maybe find the trackers which are on the pink group. So our first attempt was an algorithm called relevance search. So it's basically the only algorithm we found about analyzing, like finding communities kind of thing in bipartite graphs. There are not many out there. So this algorithm is an iterative algorithm. You basically give it a source, and then it ranks the rest of the nodes by how similar they are to the source node that you gave, based on the network position of the nodes. So we thought that if we give it a source that is a tracker, then it should rank other trackers really high, and it should track non-trackers quite low. And actually, this worked to some extent. So implementation-wise, it was really easy to write in Flink. Actually, the single source relevance search is like very, very similar to PageRank. And we also implemented a multi-source, so we gave more trackers that were like quite diverse. So we could then have a vector of scores, and then from the vector of scores, take the top K that are trackers. And that was also quite easy to write in Jelly. So this was the first data pipeline that we built, actually. We had the pre-processing step of the logs, create the bipartite graph, then run this multi-source relevant search algorithm again, and a post-processing step where we took the top K and did the classification. All of this was like a Flink program. Of course, we had to do some tuning, like these paths I was talking about before. So once we had this in place, and we had to see how to tune it to make it work better. So how many sources do we give as input? Do we give all the trackers we know, or does it make it worse? How do we define the convergence when you have the vector? Or do you wait for all your sources to converge to the last value, or you can like stop it beforehand? Does initialization matter? Or all the features that we had extracted, maybe we can use them as weights on the graph, and so on. And how do we define the threshold? So when you get a score of 0.8, does it mean that you are very similar to the tracker, or do you have to get a score of 0.9, and things like that? So actually, relevant search didn't really solve our problems. It had several issues. Like, it was really easy to find very similar nodes, the very similar few, and the very different few. So we would have a bunch of nodes with so-and-so ranks, and then like very few with really high ranks and very few with really low ranks. So we could only find a few. Then again, the source really mattered. So if we would give a popular tracker, we would discover all the popular ones. If we would give not so popular ones, we would discover the not so popular ones. But the worst thing was that we might keep rediscovering what we already know. So there is no guarantee that for the ones that we don't know, we'll get a score that will make sense. So back here, we thought about getting another path after all of this. So for several attempts that I will not go through in detail because you get the point so far, we started combining this relevant search that gave us some kind of insight with several other algorithms. So we tried classification algorithms, clustering algorithms, we tried, classification algorithms, we tried decision trees, and so on. And we had this part of the pipeline, so this was really easy to extend, actually, in Flink, and add a branch, where we added like part of our pre-processing that we had done in the beginning. Then we added several algorithms there, and then did a classification there, and then merged the results, and of course evaluate back. But this iteration happened many, many, many times, and we tried a lot of algorithms. And as you might imagine, some of them worked okay. Some of them didn't work at all. And we were more or less back where we started after this took us something like 2 months. So then we had an idea one day that we realized that from this bipartite graph that we have, all the things that we're looking for are actually in the second group. So there is no way that a user intentionally goes and visits a tracker. And these are all the pages that we have in the first group. So we thought, how can we somehow only analyze the second group? And this is what is called the projection graph. So actually, we took the bipartite graph, and we projected it so that every page that is linked from the same page on the bipartite graph forms an edge to the projection graph. So basically here, H1 and H2 are both connections that open from R1, so they're connected in the projection graph. And then here we had so many more to try now, because we don't have a bipartite graph anymore, we have a normal graph. So there are so many algorithms to try. And we were really happy to have this idea. So actually we made it work by simply running community detection on this projection graph. And the good thing about this projection graph is that it still captures the connections between the trackers indirectly through the pages that they're linked from. And what we started thinking about is that maybe these trackers form form like communities in this graph, and maybe we can somehow exploit them. So of course, we started again with basic analysis, and we started asking, like, in this projection graph now, maybe trackers have unusually high degrees, or maybe they're connected mainly to other trackers, which was actually true. Trackers are like, have 90% of their nodes are other trackers on this projection graph, which was great. And do they form connected components? And yes, they do. So this is only for 2 months, I think, out of the 6. Yes, November and December. But what we saw was that like 95% of the trackers were all fell into the same giant connected components, and the rest of the components were like much smaller and actually didn't have many trackers. So here we have a much smaller graph because we only have the one group of our bipartite graph. We have one component only that we need to work with because more than 95% of what we're looking for is in there. And we have great flexibility in the algorithms that we can try because we don't have a bipartite graph anymore. And yeah, we did this again with dataset and Jelly. But the coolest thing was when we actually visualized this projection graph. And this is part of it because it had several millions of edges, so it was very hard to visualize. But here, basically, what I'm showing is that the big red ones on this side are the very, very popular trackers. So this is like Google Analytics and things like that on this. And the rest of the white, small nodes are just regular websites. And all of this cluster on the right is all trackers, but they are the ones that you don't know. They're the small ones, the ones that relevant search couldn't give us because it would give a medium score and we wouldn't know. But they cluster so nicely in this projection graph. And the white ones in the edge of the cluster are ad servers. So we can clearly see here that if we run a clustering algorithm, we will get great accuracy. So we built a new final data pipeline where we had the logs preprocessing and creating the bipartite graph with the dataset API. And then we run largest connected components to, connected components to get the largest one with Jelly, create the projection graph, and then run community detection again with Jelly, and a post-processing step with dataset API where we took the communities and labeled the nodes that we didn't know what they are as trackers or not. And that was actually a quite small Java program, really. It was something like, I don't know, 500 lines of code if you use the Jelly library methods. So that was great, actually. So I will conclude by giving you some lessons I learned through this process, and maybe you'll find them useful. So first of all, start simple. I would say, okay, don't try the fanciest algorithm that you've heard of just because you can. Start by just analyzing your data step by step and then figuring out on the way what you need to do. And exactly choose your features incrementally. So needs for new features will come on the way as you process analyzing your data. Visualize your data. This is like extremely important if you can. Sometimes you cannot. Maybe you have too much of it, or maybe it's not in a form that you can visualize. But if it's a graph, it usually helps. Try different data representations, or try to project your data like we did. It just gives you a totally different perspective on your problem, and it opens paths to new algorithms. And reevaluate your model. So we actually used this 6 months, but we use the 6 months like month by month. So we had 3, and then we got the 4th one, and then again reevaluated if what we had actually worked with the 4th one, and then the next month we got another month of data, and so on. And this will keep on growing. So you need some mechanism in your application to reevaluate what you have when you know that you will have more data coming. And final, and my biggest advice is use a flexible system. I would say use Flink, but not necessarily. Use something that, well, first of all, lets you do this iteration over your pipeline. Like we built, I don't know, 10 different pipelines for this problem, but we didn't really build 10 pipelines from scratch. It was a matter of, taking an algorithm out and then putting another algorithm in, or maybe rewriting a little bit our pre-processing so that we get more features in, or rewriting a little bit the post-processing. But it was easy to do because we were using one system, right? So this is very important. We didn't have to connect to external systems or write to the file system through the steps. So that was really easy to iterate over our pipelines. And second, it was really cool because it let us do the testing locally. So with a subset of data, that's extremely important as well. And you could write this complex pipeline. So you could do the pre-processing and the graph analysis and the post-processing with the same system. So use a flexible system. And that's it from me. Thanks a lot. I'll be happy to take questions. No?
Which tool did you use to generate that nice visualization?
That was Jeffy. Gephi or Jeffy, yeah.
Okay, thanks.
But it had to run all night to get this, yes. There.
I know this is not the point of your talk, but I'm kind of curious now. What was the resulting numbers you got for the detection success rate? Or?
Yeah. So actually, because of this very nice clustering we saw there, something really simple like looking at your first hop neighbors in the projection graph gave us accuracy of something like 80%, which is amazing. But if we just do a simple community detection, label propagation kind of thing, we could go up to 95 and very, very small false positive rate, something like 2%. So they're really, really clustered together. And the great thing is that they cannot change the way they operate, because in order for a tracker to be successful, it has to be connected to other trackers. Otherwise, they cannot share information. So the good thing is that it's a very fundamental property that we're exploiting here, and it's exactly what gives them away. So this is really cool, I think.
Okay, thank you.
Thank you. Nope. No? Okay.
I have a question. Do you think it's possible to use streaming for this solution and have a real-time detection system?
Sorry, can you...
Sorry. Do you think it's possible to use streaming process to do real-time detection?
Yes.
Of the new? Because if you want to be... if an operator, because it's driving actually, try to block this kind of system, they will use the dynamic IP and use a very, very quickly changing system.
Yes, so this is our current work actually. So the easy one, the one that the classification that only looks at the first hop neighbors, this is very easy to do. And actually we're working on that because it will be much more valuable to have this real time. Because, okay, so the thing is that the solution they had so far, or they currently have, is that they had this list, and then once per month, yes, run it, and then, so what we have now is much better than the current solution, but we can, of course, do it real time and do it with streaming, and this is what we we are working on now. The one classification, the one that with the lower precision, is very easy to do because you need very small state to keep and update. The iterative one is not so trivial, actually, because you need to find some kind of incremental algorithm. Otherwise, you will have to like take a snapshot, run it, and then, so it won't really be real time. But we're thinking of having something in the middle, like the simple one running streaming, and then the batch one running once per day or something like now, and then somehow combine the results. Yeah. Okay. Okay, thank you very much.